continuing the seminar for energy transmission in half-wavelength lines. The next talk is going to be about a study of connection of continuing the seminar. The next work is going to be presented by Professor Luiz Carlos, and the title is Study of the Connection of the Hydraulic Plant of Belo Monte to the National Integrated System using the alternative of transmission in half wavelength. Professor Luiz Carlos, he majored in electrical engineer by the Federal University of Goiás. Sorry, not in 1945, but rectifying in 1995, not 45. He did a master's in Unicamp in 1997. His PhD also in Unicamp in 2001. Professor Luiz Carlos is a professor at Unicamp since 2002, and he also worked as a visitor professor at the Polytechnical University of Denmark in 2008, CNPq researcher, and he has received the Zephyr Novaes Researcher Award in 2012. Professor, the floor is yours. Thank you, Marcus. Well, everyone, this work, differently from what was presented before, we are trying to study an half-wavelength link connected to the National Integrated System. We saw a lot of works where the line was studying in an isolated way, just as a system, or using equivalents from a system on one side or on both sides, as we had just seen. But in this case, we are using a half-wavelength line and considering the whole of the National Integrated System, studying the possibility of use of half-wavelength from transmission of energy from the hydroelectric plant from Belo Monte. This study was already studied by EPE, and what we are doing now is investigating more. This is a master's project by Leandro Ferreira Gomes. He could not be here presenting it, so I'm going to have to do it. But this is a continuation of the work conducted at EPE. So it's a scenario for 2019. I'm going to present a scenario. We conducted several studies considering different charging scenarios, different levels of generation in Belo Monte, different transmission levels in the half-wavelength link from the north-south direction and also south-north. I'm going to skip this context part. This was already very well discussed. Why do many countries such as Brazil, China, Russia, or the African continent are interested in half-wavelength? In case of Brazil, basically for the connection of the power plants located in the Amazon in the integrated system. About the other countries, this was already discussed today, so I'm going to skip it. For Brazil, we would have several possibilities of connecting the power plants in the Amazon at this range of 2,000 to 3,000 kilometers. So this would be the Belo Monte power plant, the Rio Madeira one, distance from the northeast and the southeast, where we have the major load centers. So there would be the possibility of using half-wavelength in some of these undertakings. So this is what we did. We studied the scenario for 2019. At that time, there was a perspective that in 2019, Belo Monte could enter the National Integrated System. Perhaps this projection has already changed, but this is what we used in the study. We studied 6 different scenarios for loading in the half-wavelength trunk, considering the whole of the National Integrated System. And we worked with 3 types of corridors. 2 lines of 800 kV, 3 lines of 800 kV, and 2 lines of 1000 kV to do this connection of the Belo Monte power plant to the National Integrated System of Brazil. All the studies were conducted at Ana Rede, the basic case assembled at EPE, as I mentioned before. So these were the lines designed at the Federal University of Rio de Janeiro that were included in the study. In 2019, our system would be a little bit different. So we consider in the scenario that the human data power plants would be already fully operating at the National Integrated System using hybrid transmission, large part of it HDVC reaching the city of Araraquara, and a large part of it in CA connecting the system, the states of Mato Grosso do Sul, and Rondônia. So we'd have the power plants in River Madeira, Manaus, the line between Tucuruí and Manaus would already be operating, and the inclusion of Belo Monte with 2 transmission segments to the northeast in HDVC and a half wavelength transmission to the southeast reaching the city of Assis. This proposal was presented in several studies from EPE at the time we were discussing the alternative transmissions for the Belo Monte power plant. There are also several reinforcement works at the 500 or 400 kV grid in the city of Assis. So different scenarios predicted for the year of 2019. The scenarios for the integrated system, we have 3 scenarios for heavy loads and 1 for light loads. The generation in Belo Monte would vary from 11 gigawatts up to 0, down to 0, 2 gigawatts, 500 megawatts. So we have a broad variation in terms of generation in Belo Monte due to rainfall and the lack of reservoir in this hydraulic power plant. So we considered the extremes of operating scenarios in the power plant, and also for consumption with 6,000 megawatts, 7,300 megawatts, a little bit more than 21,000 megawatts from south to north, 800 megawatts from north to south, 4,400 megawatts from south to north. In this situation, Belo Monte is completely shut, without generation, and another scenario with light load with a large generation in Belo Monte, sending from the southwest 7,150 megawatts. This is generation in terms of half wavelength. And in the CC link, the new CC link, bringing energy to the northeast. In this scenario, it has 3,500. In this case, the northeast is returning to the north. This as well, the south is sending to the north to cover the loads in Manaus. So here we have several operating scenarios. Some very extreme ones. So we can verify if the half wavelength operation under these extreme conditions would be reasonable or not. This EPE report see for some scenarios, especially for the ones with little load on the AC link, where the efficiency is around 50, 40, or maybe 60%. So in this critical scenario, something that came about was the efficiency of the line. The losses would be gigantic, especially in situations of light load in the line. In the situations where the load would be closer to the characteristic power, the report from EPE showed efficiency of 16, 20, maybe 18%. So this is a challenge that Professor Maia Cristina brought to us, was try to study this case and see if we could improve this performance level, especially in terms of efficiency of the line, to improve the losses. So this was the purpose of this master's thesis. This came already done from EPE. It was a ready model that is being used to represent a half-wavelength link using 35 pi segments in series. Only for the 1000 kV line we did the configuration and included, because on the EPE report there was only two alternatives, two lines of 800 kV and other lines with 600 kV, but we also included two lines of 1000 kV at the system. But always using 35 pi segments in series with a total length of 2,644 kilometers, leaving Altamira and reaching the city of Assis. It was also necessary to put the 180-degree transformers at the Assis terminal to compensate the problems with the half-wavelength line. In the base case, there was already an 180-degree transformer, and the AC link for Bahia, you can forget this thing here in the middle, but this was also modeled at the base case from EPE. Here we must remember that we're going to have parallel pathways with an interconnection between the systems, the north-south interconnection. This is something that complicates the study, because this network is going to work together with this other one. And what did we use to try to improve this performance levels, more specifically in terms of losses, but also in the current profile and voltage profiles of the lens? So we needed to adjust the taps, controlling the voltage at the terminals, both in the input and output terminals. So we are working with this. This is not a new idea. This was presented in several half-wavelength papers. So working with transformers with a large tap variation, so we could have a broad control of voltage in the two terminals as to keep the transmitted power close to the characteristic power. Something that we introduced in this paper was that we can have some gains in these performance levels by adjusting. So besides these 180-degree transformers, we could adjust this slightly to improve this performance levels. This was something that was also worked on in this project. These are data from the lines, both from 800 kV and 1000 kV. This characteristic power for each one's 100 is the characteristic power for the 1000 kV line, and 4800 the characteristic power for the 800 kV line. We already know that the efficiency of a half-wavelength line is maximum at the characteristic power, and also when the power factor at the terminals of the lines is close to 1. So these were two aspects we worked with. What we are going to try to do is, regardless of the power level you want to transmit in the line, we are going to adjust the line so that power level is as close as possible of the characteristic power. So our line was going to have a nominal voltage of 800 kV, but the operational voltage is going to vary. It can be 200, 400, 500, 600 kV, in a way that the power transmitted is as close as possible to the characteristic power. And we're going to try to make some adjustments as well. So the power factor, or the reactive power transmitted in the line, is always as close to 0 as possible, and the power factor as close to 1 as possible. So these are the two aspects we're going to work with. And these are very well known and had been already very much discussed. So what do we do here? We are going to use these transformers with a large variation range of taps. So it's a transformer from 800 to 500 kV. This is the nominal value, but I can also have it operating from 500 to 300, 500 to 400. I can variate the tap as I want. This is just a simulation. It's not easy to do this, of course. So what do we do? For each scenario, thinking about the load level I have at the link, I'm going to calculate the voltage, the operating voltage at the line, in a way that the power I want to transmit would be exactly the characteristic power. So we call this ideal tap. The ideal tap would be this one. So for example, for this scenario, where the load is not in the half wavelength is very low, I'm going to work with the line at 196 kV. It's not going to reach 800. In some cases, it's going to operate with 560 kV. So I need to adjust the tap at this position. So this is the ideal tap position. As to guarantee this, that the transmitted power is similar to, or exactly the same as the characteristic power. So we do this. However, with this wide variation of tap, when I change the tap, I change the voltage, but I also affect the transmitted power. Because when we talk about conventional transformers, the tap is always close to 1 pu. A change in the tap is going to vary very little the active power transmitted in the line. In this case, when we are changing the tap a lot, when I change the tap, I change the transmitted power. So we always need to make consecutive adjustments around this ideal tap, so we can look for the point with minimal losses and maximizing the efficiency of the line. And so we can also ensure that reference power we are going to transmit in that scenario. So here we would calculate this ideal tap for all the scenarios, considering 3 lines of 800 kV and 2 lines of 1000 kV. Here, 2 lines of 800 kV. We're going to work with a higher voltage level. In 3 lines, we're going to have to drop the voltage level even more. So what do? We find the ideal tap. We create 5 values below and 6 above this ideal tap. So we have 12 tap positions. It will be around 10% of variation around the ideal tap. And what we're going to do, we're going to scan. We fixate the tap and then variate the 12 positions in the output. Then we variate the tap in the input, and it variates on the output. So for each scenario, we're always going to calculate 144 cases, and then we're going to try to assess the efficiency and the losses in the line for all these scenarios. The results? A lot of the scenarios change or are different from each other, because this is a long-term scenario. This is a base case that it's still not very stable. So sometimes when you change the tap, and then you get one result, and then you get, when you change it again, the results are similar. So there was a lot of work trying to work with all the possibilities, because it's not always possible to converge all the scenarios. Results. By doing these adjustments, this is what we received from EPE without the adjustments for all those scenarios. So we had, this would be the losses in the line for the first scenario. 13.18%. The scenarios where the load was very low, 56% of losses. By making this adjustment, these were the results we got for that tap scan. The best result was 12.38% in this scenario, 12.43%. In all the scenarios, from 24%, you can see, we could drop the losses for 12.45%. From 56% here, we could drop it to 15%. So in all the scenarios, considering a corridor with 2 800 kV line, we could decrease losses when compared to the case we called case with no adjustments. So this is the initial conclusion. We cannot operate half wavelength line without the characteristic power, especially with low loads. Otherwise, you're going to have great losses. Here, the line was transmitting 800 megawatts, but at the output terminal, we're only getting 300. Here, the line is also transmitting 800 megawatts, but it's only the output terminal and terminal is only getting 700. So there's something happening to these figures. This adjustment needs to be made. The line must be kept always close to the characteristic power. Here we saw the voltage profile. For some scenarios, before the adjustment and after the adjustments. Since the line is close to the characteristic power, it gains that voltage profile we are used to, which is flat. This flat profile, because the line is operating near to the characteristic power. But look at this. In this scenario, it's an 800 kV, but it's operating near to 0.3 pu, 240 kV. Here, it needs to operate close to 0.7 pu, so a load which is a little larger. Here, the load is a little bit closer to the original characteristic power value, so we can make it become closer to 800 kV. It's only going to operate with 800 kV if the transmitted power is higher. The voltage profile loses this wide variation because the line is now close to the characteristic power. The current profile also improves. That's why we have an improvement in terms of losses. The current profile in the middle of the line tends to decrease when you make this adjustment. It's going to increase a little bit in terms of the current profile in the beginning and the end of the line, but it's going to be a more flat current profile. This would be the current profile without the tap adjustment and after the adjustment of the tap. So he conducted this work. He did a scanning. He did this. Of course, he has scripts. He does the scripts and the network, so he can run all these cases. He doesn't have to do this one by one. But he started doing this manually. Here, there are several results. Leandro is going to finalize his master's thesis. I can make it available with Cristina. You can check all the results he's getting. But the voltage values for the interconnected system, both in the substation of Altamira and the city of Alcis, even considering the broad variation in the tap and the voltage in the line terminals on both ends, there was not a large variation. So on the system side, there were not large changes, big changes on the voltage level on both sides of the system. And this is because the system is much more robust considering with the line alone. So the system ensures a robust voltage on both ends, and you can drop or elevate the voltage profile to operate with maximum load, minimum load, medium load as it becomes necessary. What did we notice here? What I was mentioning to you before. If we forget about resistance, we can see the power flow in function of the terminal ends. If I have a diffuser, this is going to affect the power flow, but we can see they are inversely proportional to the tap. What does that mean in a conventional line? Tap does not affect the power flow because it will always be close to 1 pu. But when I do a broad variation of the tap here, the power flow is going to change. It's not going to stay fixed. So that's why I need to change the tap and then check the resulting power, adjust the tap again, because I have a reference power that I need to include in the link for each scenario. So for example, when I calculate the ideal tap, I cannot put 6800 that was defined as a scenario. I can only get 6300. There's always a difference, especially when the load in the line is very low. This difference can be very significant. To have an effective control power in the line, it's not enough to adjust the tap. This is why we decided to conduct some studies adjusting the angle as well. So we would have in the end of the line an 180-degree diffuser with another one with 30 degrees, or maybe we can approximate the two, but in the simulation we can change this angle as we wish. This was the impact. But for some scenarios, especially for scenarios of light load, it's hard to control the power flow by just adjusting the tap. So we also showed the out of phase angle. we changed it here. It was 210 degrees and went to 220. From 180 it dropped to 165. This is a scenario where south-southeast sends energy to the north, and in another scenario we increased 10 degrees as well. So we calculated, and we can see that the impact on the power flow without adjustment is what we had. With the tap adjustment, this is what I got, but I still did not get the flow I wanted. But if I change the what's out of phase, I can improve, I get this value closer to my reference value. So what we saw, it's the same thing if we consider 2 or 3 lines. It's key for us to have the adjustment capacity of what's out of phase, so we can have more control of what we has happening in the line. The adjustment of what's out of phase help us improve the converging rate in the network. This is an example of successful calculations for conversion. From the 144 cases, sometimes we can only run 19%. Not all cases can be worked with. But when we include a scenario where the line doesn't have a lot of load, we work with what's out of phase, and we can improve the success rate in conversion. So this adjustment of the active power by using what's out of phase help us improve what's happening in the network. By making an adjustment at the phase as well, what we call the fine-tuning, what we got on all the scenarios. So you can see all the scenarios here. This would be the losses of the line by just adjusting the tap, and here the losses on line by also adjusting what's out of phase. So for all the scenarios we could bring losses for these standards of 12 or 13% in all standards by adjusting both the tap and what is out of phase in the end of the line. So we are working at that 30 degrees range besides the 180 degree, which is a natural correction of the half wavelength. So we do simulations and find what's the out of phase point to minimize losses. So this would be, even if it is a manual work, this would be the operating point where losses would be minimal for each of those scenarios, ensuring that the power flow in the line is close to that reference that's established for each of the scenarios created by EPE. Then we started working a little bit with the power factor, the reactive flow in the lines. So you are changing the tap, what's out of phase, to control the active power. However, if we minimize the transmission of reactive power, we can improve yield a little more. So we started to see what is correlated. Since this is a non-conventional line, we do not know how it works very well. We had database with thousands of simulations, so we started looking for correlations with reactive power. And we noticed that differences between voltages in both terminals, the larger the difference, the larger the reactive power would be in the sending terminal. So 2 indexes that we calculated that were very much related to reactive power. The differences between the values of voltages, and also a relation of the voltage and the sending terminal and the receiving terminal. This is a ratio which is close to 1. So to minimize the power factor or reactive power in both terminals, we need to work with voltages that are close in both terminals, sending terminal and receiving terminal. And how can we do that? By adjusting the taps as well. So we need to make the tap closer to an ideal tap so we can ensure that the line will be close to the characteristic power, and then you adjust the active power by using what's out of phase, and then you do a fine-tuning of the reactive power by using tap in both terminals, ensuring that voltages in both terminals are always close to each other. So in this way you can improve. I have already talked about this. I'm going to show you the results directly. So this is the reactive power flow in the line. By making this adjustment and changing the tap in both positions, here the tap is fixed in the receiving terminal. I'm variating the tap in the emission terminal. If I do the same thing for all combinations, I can find one combination where I have very low reactive flows, low reactive injection in both terminals. So this is going to elevate my power factor closer to 1. By adjusting the tap close to the ideal one, this can improve the reactive power profile in the line, decreasing losses and improving the performance of the line. How much time do I have? Is it over? We conducted studies for these two 1000 kV lines. The results were very similar. I can give you the thesis, but I'm going to skip to a final part where I'm going to work a little bit with injection and extraction of power in intermediate points within all the scenarios are talking about. So half wavelength line, interconnection, we started to including load and intermediate points to 1/4, 2/4, or 3/4 of the line. So we conducted two tests. For example, here you have the 3800 kV lines. It goes and reaches the same bus bar. If we remove from a single line, this would produce some unbalancement in the operating system of the three lines. So we did two tests. We're taking it from just a single line and taking from the three lines. Different amounts of distributed power between the three lines. So we worked with 550 up until 300 megawatts. And on these positions that I said, 1/4, 2/4, and 3/4 of the line. The line is optimized. We did the optimization by changing taps, what's out of phase, by adjusting the reference power we wanted. And then we do this injection from 50 to 300 megawatts in 1/4 of the line. This is the change in the voltage profile. It was not big. For this power range we are extracting. This is in the middle of the line. When I put it in the middle of the line, an injection from 0 to 300, this is for the scenario number 1, a scenario of a high generation in Belo Monte and a lot of transmission in the link. When there's a lot of power being transmitted in the link, if I do this extraction, I don't see a lot of change in the voltage profile in the line. So this means that it did not move far from the characteristic power. In the current profile, it's the same thing. There's not much change because the line is in that scenario of high load. This is at 3/4 of the line. At 3/4 of the line, we start to see a little bit more impact on the current profile. This is the current profile. So I'm going to show you how were the losses in these different scenarios. Here, in a scenario with a low amount of load in the line, around 800 megawatts, when I extract from varying from from 50 to 300 at 1/4 of the line, I can see that the power profile is going to be very different from when the profile was adjusted and optimized. The same thing from the current profile. I can see that I have a more significant impact on the current profile, because here the line has a low amount of load. So if I extract 300 megawatts, I'm going to have a higher impact. For many cases, we could not get any convergence with extraction above 300 megawatts. For example, this case only goes up to 200. We cannot go up to 300 because there was problems with the load flow in the network. And in that cases, we're removing from the three lines at the same time, same amount from each of them. What is this? I have already talked about this. I'm going to skip it. So now let's look what happens to losses when we do extraction. Here I'm extracting 50 megawatts in the different scenarios. 50, 100, 200, 300. You do not see large differences in terms of how the network is working. In some cases it actually improved the performance. The performance actually improved. So a small power extraction throughout the lines for the 3800 kV lines and 1000 kV lines has some 1000 kV results as well. We can adjust efficiency from 12 to 12%, but there was no big impact on the performance of the line. Conclusions. Do I have time? In a case with a line with large variation of loads throughout the year, which is the case of Belo Monte, it is necessary to use control methods for losses. So this is going to be done by controlling the operational aspects of the line, controlling what's out of phase. The voltage, operational voltage control show to be very efficient. It's necessary to coordinate the transformers between two terminals. This cannot be uncoordinated. So we are not concerned about building issues for all these transformers. This is just a simulation. In long-term scenarios, Antonio Carlos just showed this to us. With several power plants operating, this variation in the power flow in the line would not be so big. So this problem would be minimized. This would not bring such a complex power. The altering of taps and transformer can be used to control the reactive flow, so you can adjust the active and reactive power. The use of what's out of phase in the out of phase transformers was efficient for the control of the load for the fine-tuning of efficiency. For long-term cases with several power plants being integrated, it would be more interesting to have two 1000 kV lines, because that would have that idea of the hub, several power plants adding energy to the link. More conclusions? The connection of loads or generating units can be done as long as they work with powers up to 200 megawatts. This conclusion is more related with the diverging problems we started to find in the load flow. Another problem we would have with these taps, but one possibility would be use converters to adjust the voltage, because when there's a variation in the operating voltage in the line, would demand a voltage control in the transformer working with those intermediate loads. But Antonio Carlos has already talked about the possibility of using converters to do this. The connection in all the parallel circuits is more stable, however, more expensive. If we remove from a single line or from three lines you're going to have a better result. This was Leandro's work. He's finalizing his master's. He's going to present it in January. And I think this is a challenge presented to us, and we could achieve some interesting results. At this hour of the night, I'm Mauricio from FHJ, but at this hour of the day, I do not know if I need to remember Professor Portela and perhaps a metaphor that he once told me. I do not know if the translator is going to be able to convey the message into English and Russian, but Cristina is to start playing with electrical power, to do local insertion, or even to compete, because we know that with a DC link we reduce losses in line, and for light loads they would be gaining or beating what the half wavelength, and now we are trying to operate the half wavelength with a tap from a transformer that in the simulation works. You were joking about this, if this would be doable in real life in terms of costs. That's all I had to say. Do we need to look at this? Do we need to assess the possibility of using half wavelength with a 30% load? Does this make sense? Why did we build this large corridor to transport this large block of energy? Then the planning was wrong. That was all I had to say. Perhaps Cristina Professor Portela, he already told us off. We were together. Yeah, not too many times. I believe that the idea would be to address the possibility of having a large variation of load in the power plants in the Amazon. But the proposal is to make the half wavelength a corridor to transmit large blocks of energy in a flat way, keeping the same power at the same time. Not with variation. When the EPE creates a plan for 2019 and use half wavelength with a 50% loss, we need to show that this is not the case, that this out-of-phase transformer is a little bit more expensive because you have a variation that is not going to stay at the 10% range. You're going to open this range. But this would not be an absurd value up to the point of impacting the cost of half wavelength to make it impossible. If you need to reduce to, for example, for a bid, this is a very low cost. The transformer is not, it doesn't have such a high cost, not even a 180-degree transformer. In reality, this would not be necessary if you had a substation dedicated, an exclusive one. Since you have a substation for HVDC, you could have some machines dedicated for half wavelength, and then you would not need the out-of-phase transformer. You could also have on a 180-degree transformer. You could have some machines dedicated to half wavelength, and you would just input voltage. In the same way, regarding the out-of-phase transformer, for you to make this fine-tuning, if you need to transmit 300 megawatts in a line for 6,000, then you need to work with it. You're going to have to change the operating voltage. So let me keep my job. Let me include an electronic power in this mix. I'm sorry, it was just a remark. In reality, my opinion, when we're talking about half wavelength, I need to operate this in a flat way. If I reach a power where losses start to make it not doable, because we can do this, because in Brazil we can think about a thermal complementation. Many times the thermal complementation is cheaper than you use energy in ohmic losses. I think it's worth to thinking about other alternatives, because this global planning for this country is still not happening in an efficient way. So I criticize the planning method for energy. I believe that there is room for us to work with EPEs so they can improve the planning, because a thermal complementation in an optimized way is going to create rates that are going to make it possible for us to live when these links are turned off, when there's not enough energy for them to transmit. Because it's not correct to push it. It's not correct to joke around and say, oh, this technology is no good, it has high losses, so let's forget about it. That's not the case. I believe that there are other mechanisms, more smarter mechanisms for us to work with. In China, for example, they have a lot of coal. They can generate a lot of power and transmit it in a flat way throughout the year. In Russia, they have gas in some locations, and they can do a flat generation as well. But in Brazil, we do not have this. We have water, and it varies from 0 to infinite. So this is the case. We need to be rational and honest and say, from this point on, up to this point it works, and from this point on it doesn't. Yes, I think the correct thing to do would be to do a transmission which is very close to a flat one. talking about half-wave length line, we have two possible cases. The first case is when the power on the distant substation goes through the line and there is no connection with the normal grid. And there's another case when on the half-wave length line way there is a common network and we need to work in parallel with this conventional line. What is being said here is dedicated to the second case. I must say that in Russia, basically, there are cases when the half-wave length line must work in parallel with the conventional line. This is why these issues were very well studied in Russia, and we could present to you some results for these studies. The proposal, the idea for the seminar is to exchange information and motivate researchers both here and abroad to continue working with half-wave length. Since you have a lot of background on this topic, I'm sure, for sure, we would like to have your collaboration. I believe we could end the questions and the seminar for today. We are way behind schedule. I would like to ask if the bus can come to your hotels at 7:45. Our idea is to start tomorrow at 8:30. The new program is available for you outside. We were scheduled to start at 9, but it's not going to work. So we're going to start at 8:30. So I had requested for the buses to go to your hotels at 8 o'clock. Can I ask for the bus to go to your hotels tomorrow morning at 7:45? Because it takes some time before you can enter the room, and then we can have more time for questions. Otherwise, it's going to be very hectic tomorrow. So I would like to ask you, there's going to be a large poster in your hotel saying that the bus is going to come at 8 o'clock. This is not true. The bus is going to go at your hotels at 7:45 in the morning. I'd like to thank all of you for your participation, and we can end the seminar for today.